And he traveled by train, and so to pass the time, he would play solitaire. So he was used to working with cards and putting things in rows and columns by suit. So you had to find what is the distinguishing feature. Well, these are all clubs. These are all spades. These are all hearts. And I get down to a certain card, and I'm stumped. So I will leave a space waiting for that card to appear on cue. That's the background. So here he is. He has all the information he knows that has been reported on the various elements on file cards. And he would carry them around in his pocket. And he'd look at them from time to time and try to devise a scheme. Remember, the other people, the octaves had been enunciated, the triads had been enunciated. So here he is in his paper, and he says, at that time, I decided that it was advantageous to find a more general system of the elements. And here's my attempt. And here he has laid them all out, and he's left blanks here, question marks here. He says it's advantageous to put them in rows and to form a table. And here's the smoking gun sentence right here. And it says, finally, it came to place, according to this concocted system, and I've underlined in red, very many undiscovered members. So what does he do? He knows that he shouldn't put arsenic under. He shouldn't put arsenic under aluminum. Arsenic's nothing like aluminum. Arsenic is like phosphorus. So he takes those two facts plus the courage to leave blanks, and this is what he gives us. This is what he gives us. Lothar Meyer was doing the same thing, but Mendeleyev does something more. He says, not only does arsenic belong under phosphorus, I predict that there is an element that lies below aluminum and above indium. And I will go even further, and I will predict what its atomic mass is. So he called them Eka. Eka comes from Sanskrit, meaning one after. All right, so Eka aluminum is one after aluminum. He predicted 68 for the atomic mass. Gallium was subsequently isolated, 69.7. Eka silicon, which we now know to be germanium, 72, 72.6. He says there's an element under zirconium, and it should be about 180. He said there should be an element under boron. He called it Eka boron scandium, 45, 45. It gets better. He goes into excruciating detail. This is his prediction for silicon. I already showed you the atomic mass. He says, I predict its density, 5.5. It was measured 5.36. He says it'll have a high melting point. Well, that's arbitrary. It melts at 958, forms a dioxide, has a high melting point, and he predicts the density of the oxide of the yet undiscovered element. And he gets it right to two significant figures. And then he says the tetrachloride will be volatile, and it will have a density of 1.9, and subsequently germanium tetrachloride was synthesized and measured to be 1.88. That's why we celebrate Mendeleyev. So what we're seeing here is a big transition from just experiment and documentation to modern chemistry. And how does modern chemistry work? Well, first of all, look at the data. We always have to look around us and account for all the evidence. And this is an ethical question, people. Sometimes you get data that throw you off. And it's so easy to dismiss those data. What you have to do is have the courage to say, I've got to account for the bad data, what I think are bad data, and the data that help me build my theory. So you recognize patterns. And then you develop a model, most desirably a quantitative model. A quantitative model that explains the observations, obviously, but what Mendeleyev did is he came up with a model that not only explained what we have observed, but it made predictions. And it made predictions that can be tested. I'd love to make predictions that you can't test. Let's make predictions that can be put to the test. So this is modern chemistry. So I've told you about the table of the elements. Why do we call it the periodic table? Well, again, go back to the website, and down here is a button called Courseware. And if you click on Courseware, you'll get to this menu, the first of which preferences is periodic table. So if you click on periodic table, you can get a variety of choices. One of them here I happen to choose is boiling point versus atomic number. Mendeleyev is the one who taught us that the properties of the elements are a function of the atomic mass. So let's get that down. By the way, the Cyrillic to Latin translation has not been agreed upon. So you will see Mendeleyev's name spelled many different ways. You'll see it spelled like this. You'll see it spelled like this, and so on. And so when you do a search, it's sometimes frustrating. But I'll use various forms. So Mendeleev wrote the following. He says that the properties of the elements are, or let's say vary. The properties of the elements vary periodically with atomic mass. We'll find out later that that's almost correct. There's a slight variant on there, but right now I'm going to give it to you as Mendeleev enunciated it. So atomic number, we'll learn later, is the improvement. So that's why this says atomic number. But for most intents and purposes, we can say this could be atomic mass. So what I'm looking at here is boiling point as a function of atomic number. And what we see is it's not monotonic. It's not continuously rising, continuously falling. It seems to rise and then fall. And then it rises and then it falls. And then it rises and then it falls. And it rises and then it falls. And if you laid this out in a table, as Mendeleev did with his cards, you'd find that the local maxima all occur roughly in the same horizontal position from the endpoints of the rows. And then there's a trend going from least massive to most massive. So that's where the periodic comes. So we have a table of the elements with properties varying periodically with atomic mass. So we compress all of that information and we refer to it as the periodic table. Here's atomic radius versus atomic number. You see, the radius is high, then it falls. It rises, it falls. It rises, it falls. It rises, it falls. We're going to now go into the atom and try to understand the scientific basis for this observed behavior. And so here's the periodic table in its glory today, following on Mendeleev's scheme. The elements have been named up through. The one that you're getting hasn't got the latest information. This was named over the past summer. This is element 110, which has been named Darmstadtium, after Darmstadt. And I'll tell you why in a minute. Okay? So if you do look down at the periodic table and you get above 109, you'll see these strange notations here. UUN, UUU, UUB. What is all of this? These are elements that have yet to be isolated. They're yet to be isolated. These are elements that are unstable.